Okay, let's now discuss the Poisson heuristics, the Poisson clumping heuristics for wave extremes. As I show you in previous lectures, we were able to derive the probability that the crest C greater than H. We were able to define it as equal to the average number of waves with crest greater than h in 0t divided the number of waves in 0t. And when h over sigma is very large, this ratio is equal to the number of h upcrossings in 0t divided the average number of waves in 0t. And we have seen that this is possible, this is legal to do, because we took advantage of the quasi-determinism of wave extremes. What we found out? We show that if at time t0 I add the occurrence of an h upcrossing, h over sigma, which is very large, all the realization of my process, of the random process conditioned to the occurrence of an upcrossing at t0, they are all very close to the profile mu c of t equal, this is a time t0 plus capital T, equal to h times the covariance function divided by m0 minus w, the time derivative of the covariance function divided by mt. And the standard deviation, mu c plus sigma c and mu c minus sigma c of t is always bounded by the unconditional standard deviation. This instead is the standard deviation conditioned to an h upcrossing. Okay? So what happens when h over sigma is very large? For h over sigma very large, mu sub c is much larger than sigma c. And that's why we know that with probability approaching 1, the profile of the random field, of the random process after a h upcrossing looks like this, and there will be an occurrence of a crest. Okay, that's why now with the quasi-determinism we have a proof that there is a one-to-one correspondence between there is where I can write it. Let's do it here. 1-to-1 correspondence between h upcrossings and crests greater than h. Because after an upcrossing, I will have the occurrence, most likely, with high probability, I will have the occurrence of a larger wave with amplitude larger than h. Okay. Now, using Rice formula, you can basically compute this probability as a ratio between upcrossings. Indeed, you can show that the probability that the crest is greater than h is equal to the number of upcrossing per unit time greater than h times the interval time t divided the number of crossing with amplitude 0 above h is equal to 0 times t. So this is basically number of h upcrossings divided number of 0 upcrossings. And we know that this is equal to the number of waves, and this is equal to number of crest greater than h, but this is only true when h over sigma is very, very, very large. Okay? And then, so we have a nice formula for this, because n up of h is the average number of h upcrossings per unit time. That's why then I multiply by the interval of time t. And we know that nu of h is given by the Rice integral, probability that h is equal to h, eta dot is equal to w times w dw. This is the Rice formula. And clearly now for Gaussian processes, we have that the upcrossing per unit time greater than h are equal to 1 over 2 pi square root of m2 divided by m0 e to the minus h squared divided by 2 m0. And this is an exact formula for any level h, and from this we can derive an expression probability that the crest is greater than h will be equal to the exponential of minus h squared divided by 2 m0. But this is true for square root of m0 or h over sigma much, much greater than 1. So we get the famous Rayleigh law. And yeah, we simply exploit the one-to-one correspondence between h upcrossings and crest. Okay? So now we can derive the same formula using Poisson clumping heuristics, but now we're going to exploit the structure of the extreme near large peak, and this will give us a generic